Today's topic is distances between point and line and then between skew lines. Hopefully this won't take too long, but there's a lot of information here. All right, so first of all, distance between point and line. Okay. All right, let's say we have a line, and it can be oriented, and I always draw this. It doesn't really make any difference. We have a line that passes through space, and the line is represented by this, and we've talked about that before. There's a known point, P0, and there's a known direction, V. Okay, we have a point that's not on that line, P1, with coordinates x1, y1, z1. I mean, it goes without saying that this, I should write that down, is that this has coordinates x0, y0, z0. All right. There's a vector between these two, P0, P1. Now, the shortest distance between the two of these is at a right angle. Like, say, this. You might say, that doesn't look like a right angle, but let's just assume that it is because we're looking at this from a three-dimensional perspective. All right, now if I redraw that, I can gain a perspective where I look at the line and the vector P0, P1, and this perpendicular distance in an actual right triangle. Well, there's an angle here, theta, obviously. And we can find, because this is a known point and this is a known point, we can find that magnitude relatively easily. So the distance we're looking for is equal to magnitude P0, P1 sine theta. If all we have to do is multiply this by 1, magnitude V divided by magnitude V, and this becomes, the numerator of this is the magnitude of the cross product between P0, P1, and V. So, and this is on your formula sheet. That distance is magnitude P0, P1 cross V over magnitude V. There's also another way of getting that. You can find that angle if you so choose, and you can find that angle by dot product techniques because you know V and you know P0, P1, and then you can just use straight right triangle trigonometry to find that. And actually, we can, I'll put that on the solution sheet, and I'm going to post the solution sheet for all 5 of the problems, or what is it, 6 of the problems, I guess, whatever it is. 7, I should say. Some of them have A, B. And I'll put that up tomorrow. Somebody was asking about that, and I will. Okay. But we found, given a triangle and knowing the cosine, you can find the sine of it as well as an exact value, and I'll do that. All right. And distance between skew lines. All right, again, I've got a coordinate system, x, y, z, and we have, this time, say 2 lines, L1, and say L2. Okay, and either of these, L1 is P1 plus dV1, and that would mean that we'd have to know a point, say P1, on that line, and L2 being P2 plus dV2, and we'd have to know a point on this line. Known coordinates. All right. Well, there's a vector between those two. And that vector is P1, P2. All right, now the shortest distance between these two lines is a perpendicular distance. Now, it may look like these lines cross here, but that's not necessarily true. It's from our perspective, one's above the other, and they appear to cross, but they don't. Okay, so let's say that the shortest distance is right here. And I'll show you sort of a diagram of that here in a second. All right, actually, I'm going to go to a white background so I don't confuse anybody. Okay, and here's how this works. All right, we've got the two lines, and I used green and blue. And it depends on your perspective, but which one's over top. But, you know, like this is what that diagram sort of looked like, the green and blue. All right, obviously these two lines don't cross. But there is a shortest distance between them. And that shortest distance is, if I'm right between where my fingers are at this point. It's not ideal here because, again, in the classroom this works pretty well, but this isn't ideal. Okay, so there exists always, no matter how these lines are oriented in space, always a shortest distance between them, and it lies on a perpendicular to both of them, and that's going to be an important concept here in a second. But another important concept of this to understand the diagrams is that I can always, gain perspective whereby I'm looking at these lines as if they appear to be parallel. They're not parallel. But from your perspective at this point, and I hope this is okay from, the camera, I really can't see it, but these lines lie in parallel planes. They're not parallel to themselves. They don't cross, but they lie in parallel planes. But what are you seeing? You're looking at it from a perspective that you're actually seeing, it looks as if you're looking at two parallel lines, but you're really not. They're in parallel planes. Okay. All right, let's get rid of that white background, and we're going to redraw this. Okay. So here's the redraw. And it now looks like this. There's the blue line. That's L2. And here's the green line. And again, these are not parallel lines. They are in parallel planes. They appear parallel. I hope everybody understands that. All right, here is the perpendicular distance. Now, we could put that perpendicular distance anywhere between the two planes. These two parallel planes that these lines are on. Now, there's only one place where the two lines have this shortest distance. Only one place. And it's between 2 points that can be identified, but that is not easy. I'll put a bonus question up for this chapter. It's not going to get you anything, but it's an interesting question. And I'll also put a couple of references for some internet stuff up there. And this is a comp math problem for those of you who miss the comp math references. Well, here's one. This is a comp math problem, is to find shortest distance between lines. And, there are a number of cases that can happen here, but it's a process. And there is a process to be able to find the points where the shortest distance occurs. We won't need to know it here for what we're about to do. We just have to know that this shortest distance exists, and it can be measured anywhere between these two planes. All right, I'm also going to draw, like I did on, let's say that this is the vector P1, P2. And it has to exist given a set of skew lines. All right, the distance we're actually looking for is this distance. And this thing right here, and I'll draw this in red as well, is a vector that's perpendicular to both of these at the same time, and we'll call it the normal vector. Now, you get that normal vector by crossing V1 with v2. Now, if you remember, if I take the cross product of two vectors, what do I get? I get a vector that's perpendicular to both of them. Now, these two vectors aren't tail to tail, but that doesn't make any difference. As long as I take the cross product of two vectors, I get a vector that's perpendicular to the both of them. And remember, v1 and v2, they're not necessarily displacement vectors. They're directional vectors, and I sometimes call it the orientation of the line. It doesn't change the fact that if you take their cross product, you come up with a vector that's perpendicular to the both of them. And that is what we're looking for here. All right. So this distance, and you may recognize what I'm about to say, that distance d is the scalar projection of P1, P2 onto n, which is v1 cross v2. All right. So here, let's look at the formula. All right. Given line 1, P1 plus dv1, line 2, P2 plus dv2. Scalar projection of P1, P2 onto that normal vector, which is v1 cross v2. And that's why this is on the bottom of the fraction there. Okay. So the distance is equal to P1, P2, and I'll finish this off, dot v1 cross v2, and it's on the formula sheet, over magnitude v1 cross v2. Now, in the numerator, we put that symbol on, and that's why I wanted to write this out and put it in last. That is a set of absolute value symbols because this number up here, and it is a number, it can be negative. Remember, the dot product can be negative, but we're interested in the distance. Now, the reason that could be negative is if I take these cross products, that normal vector could have been pointing downward. It's still normal, and the distance is still found along that path. And we talked about scalar projections way back when. Okay. All right, let's have some examples here. Now, this is a good example because we've already seen things sort of like this. This was one of our problems, number 20, way back when, that had some angles in it of cubes. And you already did it, so you know some of these numbers. Okay, so I'm going to draw this cube, a unit cube, at the origin. Okay, and that, of course, is the point 111. Okay, so here's the situation. First one, distance between point and line. Okay, so that would be P1. That's a point that's not on the line. And the line that we're going to be interested in here is the line that passes through these 2 points. And that is di plus dj plus dk. Now, if I draw that, if I put that out, because a known point on this one, of course, is 0, 0, 0. So I could write this as 0 plus di, 0 plus dj, 0 plus dk. Okay. Now, what is the distance between these two things? Well, the formula says that the distance is magnitude P0, P1 cross V over magnitude V. And what are these things? Well, P0, P1 is, this is P0, that's P1. Okay, so P0, P1, let me write these coordinates up here. 0, 0, 1, because that's a unit cube. Okay, so P0, P1 is equal to, remember, endpoint minus beginning, 0, 0, just K. All right, so we need to take this cross product, P0, P1 cross V. Now, what is V? Okay, I should maybe write that down as well. Okay, on this line, P0, of course, is 0, 0, 0. V is I plus J plus K. That's the directional vector. All right, so the cross product, P0, P1. Okay, now this works out nicely because P0, P1, of course, is just K. All right, so we'll do this. I usually write the whole, well, let's write it out. Because we have zeros this time. Okay, so we're crossing K with this. Okay, so the I's are 0, minus 1. The J's are 0, minus 1. And the K's are 0, minus 0. So this is negative I plus J. Now, you should be able to visualize that and try to visualize it. I'm not going to spend any time like twisting my hands here, but you should try. Okay. And the magnitude of V is pretty easy to see. That is square root of 3. And all right. And okay. So the distance we're looking for is P0, P1 dot V. Okay, so I'm going to write this out like so. Negative I plus J dot I plus J plus K or cross product. I'm sorry. I'm not going to go back and redo this whole thing. Sorry about that. I have stopped and I'm mixing things up here. I have a couple of these videos I've stopped myself and gone back and do it. I'm not going to do that. The distance is magnitude P0, P1, which is 2, square root of 2, over the magnitude of this one, which is the square root of 3. So this is the square root of 2/3. Okay, now you may not remember this, but we've already sort of looked at this situation. If I take a look at this triangle right here, that's a right triangle, and it looks like this. Okay, and up here we have the square root of 2, and down here we have the square root of 3. And the shortest distance between this point and this thing is right in here. Now, you may not remember this, but we found this angle, alpha, by dot product techniques. It turned out that the cosine of that angle was the square root of 2/3. I don't know if you remember that one, but it is. So if you look at this, you can find this distance, and that distance is the sine, or the square root of 2 times the sine of the angle, and the sine of that angle is 1 divided by the square root of 3. So that distance by right triangle trigonometry is the square root of 2/3. And you can do that and convince yourself that that's true. It does actually work. And it's found, that shortest distance is found in this right triangle, and that should make sense to you as well. Okay, now the second example for this is based off of that same diagram. So I'm going to get another piece of paper for that one. And here, actually, I'll start it on this piece of paper and then we'll finish it on another one. Okay. So let's use that point again and consider this line right here. And this is the skew line example. Okay. All right, so the two lines this time, okay, we'll call that one L1, is equal to di plus dj plus dk. Now the second example, let me see here. I got it. Okay, I'm ready. Or the second line, I should say, the green line. Let's see what that one is. Now, what's the known point? Well, the known point is 0, 0, 1, and that is on this P2, it's 0, 0, 1. Okay, so we're using the same point in two different colors. You should be able to get that. So if I write it like this, what's the known point? 0, 0, 1. What's the direction? Only parallel to the x-axis. So we have a DI here, a 0D there, and a 0D here. So this could be shortened into, I shouldn't have written that I there. Okay, so this could be shortened to DI plus nothing there, 1K. All right, let's write down the particulars. For L2, P2 is 0, 0, 1, and V2 is nothing more than I. For L1, P1 is 0, 0, 0, because this one passes through the origin. I could have used 1, 1, 1, but that would just complicate matters. And V1 is I plus J plus K. All right, according to the formula, the distance is equal to the dot product. Well, before we write that down, let me just get the formula sheet and we'll see what we need. I apologize on that. I do practice this stuff ahead of time, but sometimes I lose my spot. Let's look at the formula. Okay, so we need P1, P2. We need the cross product of V1 with V2, and we need that magnitude. And then we're going to have to take the dot product of those things. So first thing we need is P1, P2. And that's equal to, yep, here they are. That's equal to K. Look at it. It's just a unit vector between here and here. Okay. There's P1, there's P2. Okay. V1 we've got written down. V2 we've got written down. We need V1 cross V2. Okay, so that gives us 1, 1, 1 and just 1, 0, 0. Okay, same process every time. 0 in both cases. 0 minus 1, 0 minus 1. All right, so this is the opposite of that, so that's J minus K. Okay, I'm going to go on to my new piece of paper now. No, that's not a piece of paper, that's my formula sheet. Okay, so now we need P1 P2 dot V1 cross V2. Okay, P1 P2 was K, and you dot that with J minus K. Put them both in parentheses. That's an easy dot product. Only this thing gets multiplied by that, so that's 1 times negative 1. Okay, so that is negative 1. All right, we have that. Now we need magnitude V1 cross V2. V1 cross V2 is, that's magnitude of J minus K, and that's equal to square root of 2. So the distance, absolute value of, remember that's an absolute value, P1, P2 dot V1 cross V2 over magnitude V1 cross V2. So that is 1 divided by the square root of 2. All right, let me put the diagram back up there and let's examine the situation, and I might have to get my three-dimensional mock-up out of this as well. Okay, so we've got the line traveling along here in this line. The shortest distance is 1 divided by the square root of 2. Now remember that the shortest distance for this point to that line was the square root of 2 over 3. So this distance is actually longer than the other one. Now how can that be, you might say? All right, well, here, let me go to a white background. I'll get my three-dimensional coordinate system once again. Okay, so that was I, or K, pardon me. Here's the x-axis. Actually, let me use this because we had the blue line going in that direction. All right, here is the line in question. And there's the point from the first one. The shortest distance is in this area. And it's probably not a bad idea for you to just get out a couple of pencils and take a look at this. Okay. Now here's the next situation. That's the line from the second problem. The shortest distance between this line and that line doesn't occur coming down here. It occurs from about where my thumb and forefinger are. That's a shorter distance. Now, I think it's a worthwhile thing for you to get out the pencils and take a look, because you'll see it. All right. Okay, let us talk about the assignment. And I will organize this with you, and I will post the notes from this lecture. Let's see here. Again, I try to be organized, but it is difficult at times. Okay, let's see. Okay, we've got problems 5 and 6. All right, we haven't done those. Okay, so the assignment is to do problems 5 and 6. And you're finding distances between point line and skew lines. Now, the first example for this one, you're given the point and the line. The second one, you're given a point and 2 points and say find the line. So you have to do a little bit more work there. Okay, so this number 6. Find the distance between these two lines, and you're given 2 points in each case. And then find the distance. And it says show these lines intersect. Well, you show that they intersect by